In this example, we're asked to derive the rate law for the decomposition of ozone in the following summary reaction, which is here, on the basis of the following mechanism. Now again, this mechanism may not be what's really happening, but it's a hypothesis, and then based on this hypothesis, for the mechanism of how we go from 2 ozones to 3 oxygens, we'll derive a rate law which we can then compare to the experimentally measured law. So we first begin by checking that the proposed mechanism does in fact add to the correct summary reaction. So the first 2 steps represents an equilibrium. If we look, we can see that. And then the third step is the reaction of atomic oxygen with ozone to form 2 molecular oxygens. We add these, we see there's some cancellation of the intermediate, and we end up with the summary reaction, which is correct. Next, we write the rate of reaction in terms of the species in the summary reaction. Okay, so we've only got 2, ozone and molecular oxygen, and so the rate of reaction must be equal to these expressions here. Now we identify the intermediates, which is very easy to do in this case. We've only got 1 chemical that doesn't appear in the summary reaction, and that's atomic oxygen. Okay, so we can derive the rate law by either concentrating on deriving a net rate of formation of ozone or oxygen. And we'd like to see if choosing one or the other is advantageous, that is easier, a lot less work. So the net rate of formation of ozone, we can write down, it's formed by the backwards step in this equilibrium here, but it's destroyed in the first and third steps. So there it is being subtracted off. For molecular oxygen, it's formed in the first step, destroyed in the second, and formed in the third. So there it is, formed in the first step, destroyed in the second, and formed in the third. Notice the 2 here, because oxygen is formed at twice the rate of this reaction, because we form 2 oxygens in it. Now we take a look, and we can see that both of them have 3 terms. Both of them involve the intermediate in 2 of those 3 terms. It doesn't look like there's any particular advantage choosing one over the other. So we just begin with ozone to start with. So to proceed, we need to write an expression for the intermediate, the concentration of the intermediates, and we'll do that by invoking the steady state. So here's basically the problem that we have. There's our overall summary reaction. The rate of reaction can be expressed in this way in terms of the net rate of formation of the different chemicals in that reaction. Here's our proposed mechanism, and we note that our intermediate is oxygen. The net rate of formation of oxygen it's formed in the first step of atomic oxygen, that is. It's formed in the first step, it's destroyed in the second step, and it's also destroyed in the third step. So that's what we have here. We set that to 0 because we're going to invoke the steady state. That is, we're going to say that this, and it seems quite reasonable here, that this intermediate will not be very long-lived really, and probably be quite low in concentration, as will react quite rapidly with these other species. And if we do this, its concentration remains steady and low during the course of the reaction. This will be its approximate concentration. Okay, and now we have an expression for the concentration of oxygen. We can substitute that into both of these and derive a rate law. As we mentioned already, we're going to try ozone first, so let's do that. So here's the net rate of formation of ozone, and we can see it's actually a reactant, so in the end it should come out to be negative. We've wrote this down because it's formed in the backwards reaction of the equilibrium step, that's here, and then destroyed in the first and third steps. Okay, we group together the terms involving atomic oxygen to make the substitution easier, and then we substitute in for atomic oxygen the expression we obtained by invoking the steady state. Now, to add this up, we put on common denominator, which is what we do, and then take out the common factors, which we do here, And we notice there's some cancellation, and we'll get some addition, and we find the following result. So the net rate of formation is -2 times this expression here. But to get the overall rate law, we notice we have to multiply this expression by -1/2. So there we do that, and we get an overall, of course, a positive result. And we do note that this is a complex. This mechanism gives rise to complex kinetics. Rate laws don't always have this type of form. This is our rate law. Okay, we've obtained that rate law by focusing on the net rate of formation of ozone. Let's do the same for oxygen now for completeness. We better get the same result. Okay, so here's our expression we obtain if we look at molecular oxygen. Sorry, we're focusing on forming molecular oxygen. That's one of the chemicals in the summary reaction. There it is here. Again, group together the terms involving atomic oxygen, which is the intermediate, and substitute for the expression for atomic oxygen, which we derived using the steady state approximation. Okay, we do that and then put on a common denominator, which is done here. Factor out the terms that are common in both of these and then cancel. So we're going to, this term here is going to cancel with this, and we'll end up with, there's a minus times a minus makes a plus, we'll end up with 3 of these. So we end up here 3 times this expression, but we notice that the rate law, we have to take 1/3 of the net rate of formation of oxygen to get that. So we do that, and we get, of course, exactly the same expression as before, which is entirely consistent with each other, as it should be. So we didn't make any mistakes. Okay, and that's it for this example and this video. Then next video in this set of videos, we'll examine deriving a rate law for the oxidation of nitrogen monoxide to nitrogen dioxide on the basis of the following mechanism shown here.